to be looking at the atmosphere and chapter 14. So in part 1, we'll be looking at the air pressure in the atmosphere, and we'll be looking at the construction of a barometer and other fascinating things. So the atmospheric pressure is all around us. We don't even notice it, but it's due to the fact that gravity is pulling on the molecules of air, and that's creating a greater pressure as you go deeper and deeper down into the atmosphere. Now, we live basically at the bottom of an ocean of air. We are at the bottom of the atmosphere, and so we are feeling the greatest pressure of the atmosphere where we live, down at the bottom, just like a fish at the bottom of the sea. And just like the fish at the bottom of the sea, they might not notice that pressure because they've been born into it. They're used to it. You would only notice it perhaps if you were taken out of that pressure. Now, our atmosphere is a thin layer. The radius of the Earth is 6,000 kilometers, but our atmosphere is only around 30 kilometers. And even then, most of the atmosphere is closer than that. It's within like 10 kilometers is about 70% of the atmosphere. And 50% of the atmosphere is below the level of Mount Everest, which is at 5.6 kilometers. So yeah, and 10 kilometers is only about 6 miles high. So yes, so our atmosphere is pretty thin, rather like a thin skin on an orange, like maybe a clementine or an apple, but not a thick skin like a navel orange. Okay, so our atmosphere is pretty thin, and that makes it easy for us to actually pollute it. Okay, now a person who started giving people information about the atmosphere was someone named Otto von Guericke, and he was the inventor of the vacuum pump. He was also the Burgermeister, which is kind of like the mayor of Magdeburg, a town. And this is a picture of Magdeburg in the medieval days, about when he lived there. And so there was a famous experiment called the Magdeburg experiment. So Otto von Guericke figured out that there was air pressure, and he wanted to demonstrate to people that air pressure existed. So what he did was he developed this copper ball, okay, these two hemispheres, and there was a leather ring that went between the two hemispheres, but there was nothing that joined them together, no straps or locks or anything. But what he did was he was able to use his vacuum pump to suck air out of the hemisphere. And so here is his hemisphere here, and he has 8 horses on each side pulling on that hemisphere, and yet it stays together, even though nothing apparently is holding it there. There's no glue. There's just that leather collar as to keep the air from rushing back in after he's evacuated the sphere. Okay, so what's going on there? How come it sticks? So what's happening is that the hemisphere, the two hemispheres, they're just joined by that leather collar. And once Otto had sucked air out of there, there's only a small atmosphere remaining. So there's some molecules still in there. And pressure is due to the molecules bouncing around and hitting. Okay, so there are a few molecules still in there. Let me change the size here. But outside, Otto knew that there was lots and lots of air pressure pushing on it. So what happened is that inside you have low pressure. Outside you have high pressure, regular atmospheric pressure. And so what was happening is the molecules on the outside, there were so many more of them pushing on the sphere that they pushed those two sides together. So there was less force on the inside. And this showed that, yeah, every time you take in a lung of air, as you walk around, there's air pressure pushing on you on all sides. Now, how much air pressure is that? Oh, and by the way, here's a demonstration of the Maddenberg experiment. So I have these two hemispheres, suction cups, you might say. Well, yeah, that's kind of right. Anyway, so when I stick them together, well, and then try to pull on them, there's nothing happening. They don't want to separate. And the reason is, so even though I pull on them with a lot of strength, what is holding them together? They're not bound together. I can release them. So what is providing 50 pounds of force to counteract the force that I'm pulling with? Well, that's the air molecules pushing on the outside. Because when I push these two together, they were slightly arched. And so when I squish them together, the two together and made them flat, well, then what I did was air went out. And so I was left with a low pressure region inside, some molecules, but not that many. And on the outside, though, again, high air pressure. So that's a mini Maddenberg sphere you can make out of suction cups. And that can have incredible strength. So yes, so how does the suction cup work? Well, you have to find a nice flat surface that's smooth, because you gotta make sure that when the suction cup hits it, air squeezes out. Okay, and then the suction cup usually tries to arch back up. The better the plastic is, the better the suction. So here's a suction cup where what they do is they actually use the lever to pull the suction cup back to a higher shape. That creates lower air pressure inside. So what I can do is, when I lock it onto this piece of plastic, there I can hold up this heavy piece of plastic. What I've done is created that air pressure. Okay, on the outside is pushing it on to the plastic here. And so I can pick up many things just by using air pressure. So here's a larger piece, right? A larger suction cup. Put it on this book, and now I can pick up the whole book if the book would stop opening. And so that's the idea, is that there's a lot of force that is created because of this idea of suction. And as you can see, it's not sucking at all. You have squeezed out some air, that creates low pressure, and then the high pressure of the atmosphere is holding it, squishing it towards the surface. Now, up above, there's a picture of this poor man who's been caught by an octopus, and he has tattoos, but these things are not tattoos. Those are left from the octopus, which has a similar system of suction where it uses its muscles to rise up once it's on your skin, and that creates a low pressure region inside, and the water pushing against it creates the high pressure. So it's actually pretty hard to escape if you're a fish or even a person. Okay, so where does the atmospheric pressure come from? Well, if you took a bamboo tube and extended it to the top of the atmosphere, that around 1 centimeter squared area would have about 10 newtons of force on it, about 2.2 pounds of air. Now, if we take a 1 meter squared area, then we would find that that was 101,300 newtons worth of force pushing down on this area. Remember, this is going to be pressure. Pressure is force divided by area. So this becomes 101,300 pascals. or we say 101.3 kilopascals. Now, how much is that that you would actually understand? That's about 14.7 pounds over every square inch. So if you can imagine, every square inch of your hand, of your body, has nearly 15 pounds on it, like a bag, well, a big bag of sugar, or a baby sitting on every square inch, squishing you. The thing is, you don't feel it. You've been born with it. And the air pressure doesn't push you one way because the air pressure acts equally on all sides. So you get pushed in both directions. Okay, and so you are squished, though. You definitely are in a squished position. But again, you don't notice it. You were born into it. We don't notice it because it's everywhere. And so just like the fish at the bottom of the sea, we are used to being under pressure. Now, if you take that fish up to the top of the sea, then some creatures from the depths have been known to sort of explode once they get up to the surface, especially things that are soft. So what happens to humans if you take them out to the vacuum of space? Basically, in the vacuum of space, the reason we die is not just that there's no oxygen to breathe, but it's because we don't have anything holding us, pushing on us, which is what we're used to. And so have you ever sucked on your hand and made a hickey, right? Or a bruise? Well, what's going on there is that when you suck on it, you're creating a low pressure region. And so what happens is your blood starts to rise towards the surface and you actually will get a bruise there. And that's basically what happens if you're in a low pressure situation. The blood is usually held in the veins partly by the pressure of the atmosphere around you. And so yes, you would get bruised. You of course wouldn't be able to breathe, and you can't hold your breath because your diaphragm would not be able to hold the atmospheric pressure. If you took a breath of normal atmospheric pressure, it would rip you apart trying to get out of you. So it's a really horrible way to die. Anyway, so your tears are usually held in, your blood is held in, your eyeballs are kind of held in, so they start to bulge out. Anyway, you don't explode, but it's definitely not a good way to die. And so when you're out in space, you have to wear a pressure suit. The pressure suit squeezes you with a layer of air all around your body and keeps your body working normally. But yes, space is dangerous, very dangerous. And it's not just lack of air, it's lack of air pressure. Okay, so one thing is people do tend to say sucked because we are used to this sucking motion, right? Mm-hmm. Yeah, but most of the time, what's going on is that if there's a low pressure region, high pressure is pushing something into that lower pressure region. So here we've got a vacuum pump and we've got this cylinder here held inside this chamber. And what happens is that as the air pressure is pumped out, this becomes lower pressure, fewer molecules to knock into that cylinder, but you've got lots of molecules outside pushing on it. So what happens is you've got higher pressure outside, and so that pushes the weight up. So that's usually what is happening in a sucking situation. The movement is not caused by the sucking. The movement is caused by the high pressure on the other side. Okay. So for instance, this is like one of the worst pictures in your book, which because it has this giant hand of air pressure pushing on the drink, which is really, yeah. But let's talk about how we suck through a straw. So I'm going to redraw it here. So here we've got a person. Okay, and they have a nice big drink down here, and they've got a straw, and it's a bent one so that I don't have to draw things in a weird angle. Okay, and so what happens when you suck on a straw? Well, what does happen? Well, what do? Think about it. purse your lips, okay, around the straw, because that's one thing. You need a good seal. So that's why if you've just been to a dentist or something and your lips are numb, it's hard for you to suck on the straw. And then what happens is that you actually arch the roof of your mouth to make the chamber inside a little larger. That creates a low pressure region. And so because of that, what happens is the giant fist of atmosphere, let's make you have an orange soda here. All right, so the giant fist of atmosphere is going to start pushing, is always pushing on the outside. But now, because we have lower pressure on the mouth, then what can happen is that your drink gets pushed up into your mouth and starts to fill it. And then when equilibrium is reached, pressure-wise, then you've gotten as much liquid as you can get, and then you have to swallow, right? So you suck, reach a pause point, right? Swallow, then you have to do the whole thing over again. So yes. So anyway, so that's what's going on when you are sucking. And again, it's the high pressure on the outside. Okay, that is pushing material into the low pressure region. So the same thing happens when there's an airplane. We usually tend to think, we say that people get sucked out of an airplane if a window breaks or something. But what's really happening? Well, in the window, here's the outside. Outside, when you're high up in the air, that's a low pressure region. The inside is a pressurized cabin. So that's actually at the higher pressure. So what happens if a window breaks is things get pushed out by this higher pressure. And so, so things go flying, but it's only loose things that are being pushed by the air as they rush towards there. And once equilibrium is reached, then of course things are going to stop flying out. So usually people are perfectly safe as long as they're not too close to the window. Okay, now a barometer is a device to measure air pressure. And so the old kind that used to be used was a mercury that was a large tube of mercury. And this tube is usually like a meter long. And what happens is that that's upended in a basin of mercury. And so it's what happens is that the mercury that's in the tube drops down a bit. Okay, and what's up here is a vacuum. No air is allowed to, no air bubbles go up. It's just a vacuum up at the top. And people say vacuums suck, but again, a vacuum is nothing. That's exactly pretty much what a vacuum is, mostly. So anyway, so it's nothing it's a place that things can be shoved into. It's like a nice clean closet that you found. You know, sometimes I have dreams about closets. It's like, oh, I found a closet. I can put stuff in it. Well, that's the idea here, is that you can put stuff into a vacuum, but it doesn't actually suck. The closet doesn't come and get your stuff. Okay, so anyway, yeah, my house is short on closets. That's the sort of dreams you have when you're older, closet dreams. Okay, so anyway, so what happens with this is there's a certain force, a weight of the mercury, and the mercury drops down until there's an equilibrium. Now, for normal atmospheric pressure, which we talked about how it was 101.3 kilopascals, that is what we also call 1 atmosphere. There are a number of different ways to measure atmospheric pressure because weather people and use a different system than physicists, and so there are lots of them. But 1 ATM is just a nice way to say 1 atmosphere. And remember, we talked about how that's around 14.7 pounds per square inch. Okay, well, when you're talking about equal to how many millimeters of mercury, it's equal to 760 millimeters of mercury. Now, 760 millimeters, that's 76 centimeters. And 76 centimeters is big, right? So think of a meter stick. This is a 75% of it. And I used to work in a lab that actually had one of these, and it was fascinating. You had this giant tube of silvery mercury hooked onto a rack. And you know, it was just, I had to take actual readings off of that giant barometer. So what goes on is that at this point, the pressure of the atmosphere balance is 760 millimeters. But what if the weather starts to get worse? Usually worse weather, you have a low pressure region. That helps bring clouds and rains into that area. And so the pressure might lower. Maybe it goes down to 730 millimeters. So more liquid flows into the dish. Okay, but it balances out the atmospheric pressure. So you would read it and say, oh, the pressure has dropped to 730. Okay, so they're balancing out. Or you might be headed for some exceptionally good weather. Usually that occurs when there are higher pressure regions, basically pushes the clouds away. So maybe the weather is up to 780. Okay, so this is when people, you've probably heard of Mercury rising. That's when, or people talk about, the pressure's dropping. That's the idea. You're actually dropping inches of mercury or centimeters of mercury. Now, of course, most of the time we don't use this kind of barometer because how many places have room for a giant tube full of mercury, which, by the way, is not so good for your brain. So usually what they do nowadays is they have a diaphragm, basically a little pillow that is filled with some air. And what happens is that there's springs that are sensitive that are hooked to it and stuff. And when the pressure is lower, it swells up. And when the pressure is higher, then it gets squished down flatter. And so those springs are sensitive to the motion of it, and that turns into a reading, either a digital reading or a dial reading. So a lot of barometers do not use 760 millimeters of mercury. Okay, now we have just lived through a pandemic. And obviously, if you're listening to this, you lived through the pandemic. There were other epidemics in the past. One of the worst ones was the polio epidemic. And again, that was solved by getting vaccinated, right? Your polio inoculation, which you probably have gotten. And the thing is, the polio epidemic struck down thousands and thousands of people, mostly children, but adults too. Franklin Delano Roosevelt could not walk well because he had been attacked by polio. And this is a ward during those days. And what are those things? Those are iron lungs. What's going on with those? Who's in those? Well, people had to go in them because the polio it would keep you from being able to move. Of course, so you might have your arms and legs, but it also attacks your automatic system, so you might not breathe. So the iron lung is to help you breathe. Okay, so here's a girl in an iron lung, and it's very much like the Maddenberg experiment in that she's in a big metal pipe here, and she has a leather collar or rubber, maybe if they had it in those days, around her neck to keep the air pressure in. And what would happen is that when you're a human, take a breath. What makes the air move into your lungs? Well, what happens is your ribs expand. That reduces the air pressure in your lungs, and then air goes down your throat. Okay, so your ribs, your muscles around your ribs are really important for you to be able to breathe, and your diaphragm and stuff. So what happens here is she can't breathe that way. So what they have her in is she's in a vacuum chamber. So the vacuum chamber gets evacuated, And then what that does is her ribs expand. That creates a low pressure region. And so then the air goes down into her lungs because her ribs have expanded. Okay, so that's what's going on. It's creating a low pressure region in here, and then the air rushes in. Nature abhors a vacuum, they say. And what nature does is it shoves things into a vacuum, just like you would put things into a closet. So anyway, so then when she wants to breathe the other direction, breathe that breath out. Then there's high pressure that squishes the ribs together. And so this is going to go on every few seconds and until she recovers, hopefully. And there was one woman who never really did recover. She was like in an iron lung type thing for 40 years. And they eventually learned how to make small ones that you could kind of wear on you. So it would be kind of like you were wearing a life vest, only it would squeeze your ribs and then pull them out and squeeze and pull. And that's how you'd have to live if you wanted to live. So anyway, so make sure you get your vaccinations, because it's just as important now to get vaccinated as it was then. That was an amazing thing, the polio vaccination. Okay, so now nobody worries about polio, but well, at least not very much in this country. And they almost wiped it out of the world. Okay, so that's the end of this. And don't forget to get your shots. All right, so we're going to stop. Okay, and we'll be going on to part 2.